Hello, welcome to the week 17 lecture, which is all on the topic of testing. So before we begin, I'm just going to mention some important things about the upcoming assignment. So in tutor week, which is in week 18, next week, by Wednesday, 11:55 p.m, you should submit a formative copy of your assignment. So formative means it's just a chance for us to look at it, give you some feedback on what you've done so far, how you can improve your grade, the strengths or weaknesses of your submission. So you should really try and submit what you've done so far in order to receive some formative feedback. If you haven't started your assignment, now is the time to do so. So even though the portfolios are due in before the assignment, make sure you are making some decent headway on your assignment. Just to remind you about the marking scheme. So this is the marking scheme for the assignment, and if you look at each of these rows, just get the laser pointer out. So each of these rows corresponds to a base mark. Now, what this means is, in order for you to, let's say for example, get 100%, not only do you have to incorporate inheritance and play a character with collision detection on multiple levels, you also have to include everything else before that. So you need to work up in a linear fashion. You need to make sure the game's working. Is there some sort of goal on the screen? Do you have at least one enemy who moves towards that goal? And is the enemy clickable? And so those four things would guarantee you a mark of 40%. Okay? That would guarantee you the base mark, 40%. If you want to get the higher range of that bracket, i.e., towards 50, you'd have to incorporate all these four things, and then you would have to incorporate many of these coding concepts. Okay? So just to go back on that other slide, if you've got a working game, a goal on screen, one enemy moves to the goal, enemy clickable, that gives you 40, and then to get a higher range, i.e. towards the 50, you need to start incorporating some of these good programming concepts. So it usually goes without saying that you are going to have multiple classes, and those classes should have constructors, just so you can instantiate those objects. Each of these classes will have methods, and then in terms of things like polymorphism, we'll cover that before the final deadline. So you've already covered a lot of these things, so constants, final variables, the use of functions such as a method that returns a boolean, comments, well-structured indentation. So these are the things that we've covered along the first and second terms. So make sure when you're looking at the marking scheme, make sure you don't miss anything out, because if you implement everything, all these things, but you suddenly forget to have an array of enemies, that means you're not eligible for anything on this row. Okay? So let's say you implement everything on that first and second row, and you implement an enemy animated sequence, you implement a game over message, and the goal must be smaller than the screen, width and height. But let's say you've not implemented the array. In order for you to meet that base mark of 60, you have to meet all of the requirements for that row. Okay? So that's really important. The most important part of this assignment is to read the spec and make sure you are implementing things in a logical order. Anything else? So what I would highlight with inheritance as well is make sure your inheritance relationship makes sense. So don't just add the extends keyword just for the sake of it. In order for you to meet the inheritance criteria, you need to have an inheritance relationship that makes sense. So last year the assignment was a fishing assignment where they had to create a boat which had a hook, and then that hook had to fish for fish. And some of the inheritance relationships were things that didn't make sense. So, for example, class fisherman extends boat. Okay, so that doesn't make sense. So a fisherman isn't a boat, and a boat isn't a fisherman. The only things those classes would have in common is perhaps an x and y value for the location. So if you want to define some sort of superclass which defines x and y, such as a sprite superclass, and then you could create subclasses which extend that functionality. Okay, There are other ways of implementing inheritance. So, for example, you could have some sort of zombie class, which could be the superclass, and then you could create a more specific version of that superclass called Crazy Zombie, which is faster, maybe a different colour, maybe it walks in an unpredictable way. So don't forget, the subclass is always a more specific implementation of its superclass. So the superclass is usually quite abstract, and then as you go down the inheritance hierarchy, you get more specific implementations. In terms of the splash screen, that can literally just be a welcome screen, just to say welcome to the game, press space to continue, and then it will continue and give the player options to play the game, such as maybe difficulty levels, or you could have another screen that says controls. But in terms of meeting this criteria here, splash screen, that could just be a screen to say welcome to the game, press space to continue. Okay. So if you have any questions about these criteria on this spec, make sure you are asking your lab tutor, going to the drop-in session, just to get clarification on any of these if they don't make sense. Okay. And again, those are the good programming concepts. So those things here, if you will implement them, they will increase your base mark in that range. All right. Moving on to the portfolios. So the portfolio cutoff date is the 8th of March. That's on the Friday, which means if your lab is on a Friday, the 8th of March will be your last day. And then if your lab is on a Monday, the last chance you have to get things signed off will be the Monday. So we can only guarantee that things will be signed off inside your scheduled lab classes. So, for example, if you're in a lab on Thursday, you can't just sneak into a lab on Friday and get all your portfolio signed off. And we have to give every student a fair opportunity to get them signed off. So, for example, if you've just strolled in on the final week, week 21, and then you come in with 7 portfolios, the chances are we may not be able to sign off those 7, because we need to make sure every student has got an equal chance of getting things signed off. Okay. So get the pen out. The first portfolio was the colliding objects. That was a fairly difficult one. That was the first one we had that involved creating a collision between 3 objects on the canvas. And then the second portfolio was the defenders. That's where we had the alien class and the defender class. We created 3 objects of the alien class, so we had 3 instances. And then we made sure the aliens could crash into the defender. And we also should have incorporated a game mode variable. So you should have done that for the portfolio. So those first 2, those are the processing portfolios. And then everything past portfolio 2 is implemented in Eclipse. So portfolio 3 was to use a switch statement, type in a integer from 1 to 12 to represent the month, and then you would type in another integer to represent the day, and then you would check to see if that day was valid for that month. Portfolio 4 was the tiled room. That's where we had the room superclass. So when you started the portfolio, you would have created a class called tiled room, which hopefully extended from room. And then for the portfolio to be signed off, you had to override the calculate cost method for that tiled room and call the superclasses calculate cost method, and then just pass in the additional information such as the cost of the grouting or the additional time required. So grouting was charged at the area. So if the area of the room was 20, the extra price there would be 20. And £20 for the grouting. And if it's a tiled room object, then they also get paid a multiplier of 1.5, so they get time and a half if it's a tiled room. And then portfolio 5, which is in week 16, that's the ASCII art portfolio. So if you did the lab, which was converting a cat image to a grid of ASCII art characters, The ASCII art portfolio was just a case of changing the cat image to the image of Mona Lisa and then creating a 2x2 pop art grid where each of the images, so the first image would have been a normal Mona Lisa, and then the second image to the right of that would have been an inverted one, and then for the second row those would have been flipped around. Okay, so for a representation of that, make sure you look at the lab sheet and it makes it very clear as to what you need to do. So Portfolio 6 is this week. This is week 17 in this lecture. So I'll talk more about the portfolio at the end, and you should also introduce yourself to the portfolio in the lab. So as you can see, there's 7 portfolios. Just a quick note about Portfolio 7, which is on graphical user interfaces. It says week 20 here, but we've decided to bring that forward to week 19. The reason we've done that is there are some labs who have their labs before the lectures, which means technically they don't do the lab until the week after most of the other labs group do it. So obviously some people may think of themselves at a disadvantage in terms of, you know, they've got one less week to do it, but this is just to guarantee that those labs who have their lecture after their lab are able to see that assignment or to see that portfolio a week before intended. Okay, so the portfolios are due in on week 21. So for those labs who have their lecture after their lab, for those guys it would have been week 21, which means they would have had to have done the portfolio in that week, which isn't really fair. So what we've decided to do is bring the GUI portfolio a week in front, just so everyone's got a chance to see it a week earlier. Okay, so after you come back from Tutor Week, you should be able to see all of these portfolios, and hopefully you've got them all done in time. So any questions about the portfolios, make sure you ask your lab tutor, or send me an email, or visit the drop-in sessions Monday, Wednesday, Friday, 12 till 1. Okay, so now on to the actual lecture. So this lecture is on testing. Specifically, we're going to talk about the philosophy and the approaches to testing, focusing on the 2 main types of testing, which are black box and white box testing. Those terms are quite broad, so we'll see examples of black box and white box testing in the lecture. And we'll talk about some strategies to use when testing, specifically equivalence partitioning and boundary value analysis. Okay. So these are some quotations which sort of illustrate the importance of testing. So testing shows the presence, not the absence of bugs. Bugs lurk in corners and congregate at boundaries. And that last quotation I'm not going to read out because I probably going to have some trouble pronouncing that word. So that last quotation is just to illustrate, you know, when we're testing for the extremes. So a QA engineer walks into a bar, orders a beer, orders 0 beers, orders, you know, millions of beers, orders a lizard. That's just to give you a representation of what we're trying to test for here. So we're testing for these extreme cases. So orders a beer should be valid. Orders 0 beers, that sounds a bit dodger, so that should be invalid. Orders that many beers, that should be invalid. Lizard should be invalid. -1 beers, invalid. Orders that word should be invalid. So that's to show you there the extreme cases we're trying to look out for. Okay, so what is testing? So the aim of testing is to check the quality of a piece of software. And when we say quality, we mean a few different things. So things like the functionality of a piece of software, the reliability of a piece of software, the performance of a software, whether that's in terms of speed or responsiveness, and generally anything which is specific to the requirements of that piece of software, whether that be the customer requirements, you know, the functional requirements, the performance requirements. So requirements is quite vague. It generally encompasses a lot of things, and we'll see that in this lecture. So testing involves performing a series of experiments on software in a controlled manner, and because it's in a controlled manner, that means testing is usually a planned activity we don't just create pieces of software and then decide at the end, oh, maybe we could test this. You know, the mindset should be, as you're coding, oh, how could I test that this works? And there are, you know, programming, you know, paradigms such as, you know, test-driven development, which focus on creating a test to test some logic before you actually code the logic, which may not sound, it may not make sense that how can you test something before you implemented it? And that's the idea between things like test-driven development. That's outside the scope of this lecture. But just to make you aware, there are some strategies used for testing which may not sound logical, but they are logical if you think about it, because in order for you to code some logic, it makes sense to test that logic before you've coded it. So if you want to do some research on that, if you just do a quick Google search for test-driven development, that should hopefully explain it in a much better way and give you some idea as to what that is. Okay, so when we talk about errors in software, we're typically referring to any non-trivial piece of software, and any non-trivial piece of software is unlikely to be completely free of errors or bugs. The typical error rate is 0.5 errors per 1,000 lines of code in a shipped product. So as you can probably tell, shipped product as in the product has been shipped to the client or customer. So we can't make the assumption that everything we write is going to be completely error-free. We can just hope to fix most of those errors during development. So during development, typically 10 to 100 times that number of errors are corrected, which is good. We want to correct the errors as we're coding, and hopefully we don't pass on any errors to the shipped product or the completed product. And the cost of errors, as you can probably imagine, during development, the cost of errors are relatively cheap in terms of time. But after you deploy a piece of software, after you ship it out to the customer, those errors can be very costly. So if you're required to support the software that you've just shipped out to the customer, the error is going to be very costly, because this may result in some downtime for your clients' customers. So they may need to bring down some of their services while you try and get that fixed, or whilst they try and get it fixed. So errors are very cheap to fix during development, but as the development lifecycle continues and you've shipped out the product to the customer, those errors can be very costly to fix. So in terms of the types of testing, we have these very broad terms. So things like static types of testing, these are typically offline procedures which don't actually require us to run the code. And then the opposite of that is dynamic testing, where we are performing experiments on running code or parts of it, usually with a predetermined test plan, and this is sometimes automated. Now, there are 4 general levels of testing. Some of these are static and some of these are dynamic. So focus first on usually the smaller part of levels of testing, so unit testing. So unit testing is where we're testing individual components. That can be something as small as a method, or something as big as a class or a program or a collection of classes. So we're testing there mainly for the logic. So does a method accept inputs? Does it provide the correct output? So that's typically on smaller pieces of code. Just above that, we've got integration testing, which is testing or combining components or units, and we're testing there for the interface defects between those components. So do they integrate well together? Are they communicating in the right way? You know, when a method calls, you know, a method from another class, is the correct output being obtained? Now these two at the top, this unit testing and integration testing, as you can imagine, these are carried out by the developers. And these are often automated. If you've been exposed to testing before in Java, you've probably heard of some frameworks which help you with these types of testing. So for example, unit testing, you can use a framework called JUnit, which is available inside Eclipse, and you can use JUnit to actually perform some unit tests. So performing unit tests is actually outside the scope of our course. We're just introducing it. It's outside the scope of this unit, sorry, but we're just introducing it in a high level. So you may do some unit testing on your second year if you take the advanced programming module. Okay, and then going on to the higher levels of testing, these are typically done towards the end. So system testing is testing the system as a whole, so testing all of those units, testing with reference to the requirements, okay? So the functional requirements, the customer requirements, and then the final one, which is typically done at the end, is acceptance testing, which is testing the final system. And the aim for acceptance testing is to determine whether the system is ready for deployment. Okay, so you may have heard of user acceptance testing, which is testing to see you've met all of the customer's requirements. So the customer may say, or the user may say that they want a GUI, and the GUI has to be this color of blue. It has to be this hexadecimal value of the blue to match our logo. So it could be something as trivial as that, making sure it's ready for deployment in terms of all those requirements. And those last two there, those system testing and acceptance testing, those are typically carried out by a test team, and quite often those are external. So someone external will test to see if you've met those requirements. So those are the 4 levels of testing, and these levels of testing can be further divided into black box and white box testing. Now when we say black box and white box, that refers to the accessibility of the internals or the code of the software when designing the testing strategy. So if you attended last week's lecture on sorting, we covered the sort method from the arrays and the collections classes. So the arrays.sort method and the collections.sort method that we saw last week, we treated those as black boxes because we didn't really know how those methods worked. All we knew is that those methods existed and we could call those methods. So we'd say arrays.sort. We didn't really know how that sort worked, we just knew it existed and we know what it did. So in this case, black box testing is treated as a black box of software. So we know what it should do in terms of the requirements, but we don't really know how it does it. So with black box, the word black there is just sort of insinuating that we can't really see inside the box. So we don't really know much about the internals. And tests for black box testing are designed from this knowledge of the expected behavior. So again, we know what the software is trying to do, but we don't know how it does it. Whether that's a particular method that does something, we don't know how it does it. Now, as you can imagine, white box testing is the opposite of that, where we have tests designed with full knowledge of the code. And the aim for white box testing, the aim for white box testing is to test paths through the code. And the aim for white box testing is the coverage of code rather than the coverage of any inputs. I like to call white box testing glass box testing, because with glass you can see through it. Okay, so with black box testing we can't see inside the internals of the code, but with white box testing or glass box testing we've got full knowledge of the code, so we know exactly what's happening. So as you can probably imagine, white box testing is probably going to be carried out by the developer because they have knowledge of the code, whereas black box testing is going to be carried out by someone who may not have knowledge of how the code works. Okay? So in terms of the testing lifecycle, in terms of where we start and where we end, as unit testing is usually carried out on the smaller pieces of code, such as the methods and the classes, we typically perform those first, and then as we get deeper into the life cycle of testing, we then perform integration testing on those different units, then system testing, and then acceptance testing. And then, as you can see, each of these 4 levels of testing encompass these different techniques. So you could actually use black box testing for either of these, because you could assume that you don't know how any of the units work or how the system works. And then in terms of the people performing these types of tests, for unit tests and integration tests, it makes sense for the developers to carry out that, because unit tests implies you've got some knowledge of the code. You may not have knowledge of the code, so you may be testing a unit which you've not implemented yourself, so that could be black box. And then in terms of the system testing and acceptance testing, that's typically black box because we're testing the system as a whole, and the person who usually carries that out are testers as opposed to developers. So testers may not have full knowledge of the code. In companies, big companies such as Barclays, they'll have a whole team of people who are just there to test the software. So these testers may not be the best programmers. They may not even know any programming language in any great detail. They're just there to test the code works or the system works. So it's not usually good practice to let the developers test their own code, because these developers are going to be biased because they're going to think their code is great. They're going to think their code works, and they may not provide exhaustive testing. So that's where the testers are going to come at the end and just make sure everything works as it should do. And all of these are usually based on the requirements. Unit and integration are usually based on the requirements and the design. Okay. So I'm going to start by talking about static testing procedures. Now this is the most common type that we do in the labs. So static test usually happens offline. So the most common type is static analysis, which is where we could use automated tools. So one tool is called Lint, which is one of the things available in the Unix operating system, which checks code before you run it. And it checks things which are quite common problems when we first learn how to program. So, unreachable code, variables which haven't been initialized yet, and suspicious looking code. So think code which looks a bit dodgy. So did you really mean to type that code in? So missing semicolons, variables which haven't been initialized is quite common. And unreachable code, we'll see an example of that now, because unreachable code is hard to explain without actually viewing an example. So what I would encourage you to do now is just pause this video and just try and find out why this crash method name has a red underline and why this I++ has a yellow underline. So hopefully you use those seconds to pause the video and try to establish why we have some errors here. So we'll start with this crash method name. So we're stating here that this method is going to return a boolean, i.e. true or false. But what if this for loop here never actually executes? So for example, this boolean condition here inside the header of the for loop, what if that never evaluates to true? And if that never evaluates to true, we've got two return statements here, and those return statements are inside the for loop. So let's say we call this crash method, and this for loop never executes. That means these return statements never get the chance to execute. So we'll essentially get trapped inside this method because we've got no chance of returning if this condition is never true. And then in terms of this I++, this is referred to as dead code or unreachable code. The reason we call it that is, if you look at this for loop here, let's say this for loop evaluates to true, and then it does something such as get the colour of a pixel, and then it has an if statement. So if the colour of the pixel is equal to the same colour as alien 1, or that coloured pixel is the same as alien 2, we can return true, else return false. So if we get to the point where we're running this if statement, it's either going to return true, and if it doesn't return true, it's going to return false, which means we never actually get a chance to increment that counter variable. Okay. So to fix this method, you would just get rid of that else statement and put that return false after that for loop. So that for loop will check to see if the pixel is equal to alien 1 or 2. And then instead of having the else return false, you could just have the return false here after the for loop. So if it doesn't get a chance to return true after running that for loop, it will eventually return false. And that will fix both of those errors, because your method will eventually return false if it doesn't get the chance to return true. If you need an explanation of that code, make sure you go back to week 8. or week 9, I think it was actually, where Kevin Tan, and then you've got the lab solution for that video as well, which talks you through that code snippet. You would have implemented that code snippet for the second portfolio, so hopefully you've already done the second portfolio and you know what this code does. Okay, so going on to more static testing procedures, the 3 that I'm just going to quickly talk about are code reviews, code walkthrough, and pair programming. So with code reviews, it sounds as boring as it is. So it's a formal procedure where programmers read through the code explaining what it does. Typically when we do this, we're essentially trying to debug our own code or test our own code works by trying to walk through it in quite an informal manner, because we're trying to just read through our code and trying to say what it does. Okay, so we're not really using any tools here because static involves an offline procedure. So code reviews or code reviewers will try to spot flaws in the implementation and play devil's advocate. And this can be quite time consuming if you have a large program. So in the programs that we create in the labs, these are quite small, and our code is typically contained in 1, 2, 3 classes. So this isn't time consuming for us, but as you can imagine, for a huge program which has a huge collection of classes and methods and many different branches where the program can go, this will be very time consuming to actually walk through all of the code. So another example which is similar to code inspection and code review is called code walkthrough, which is where you mentally execute the code. For example, you're performing those calculations. So if you've got, int I equals 0, you'll try to mentally execute it and you'll try to create the variables in your head and try to flow through the code. And as you can imagine, that also isn't practical for large pieces of code, because you could have a method which is doing quite an advanced calculation which isn't practical to do inside your head. You may have a method which calls another method if some condition is true, else call another method if that condition is false. So if you've got loads of different branches where your program flows, that's not going to be very practical for large pieces of code. Again, we can get away with code walkthrough in the labs because our code is typically small and contained to a couple of classes. And those 2 approaches are fairly related to pair programming, which is where a pair of programmers will work in pairs, one typing and the other observing and checking the code. So that could be 2 people of the same seniority, such as 2 developers. One could be a senior developer who just shadows that junior developer to see if they're doing things okay and writing the code efficiently. Again, that is time consuming because it makes the assumption that one person is going to be typing out the code and another person is going to be observing and checking the code as the person is typing it. So again, that could be quite time consuming in that regard. So just to talk about the black box testing strategy, we need to, how do we go about designing a test case for a black box test plan? So the most common approach is to analyze the input domain. So, for a method, what are the inputs for that method? And then for each of those inputs, identify what's known as an equivalence class partition. And this should divide up the range of possible values of an input into ranges of values which should be processed in the same way according to the specification. What I mean there is, essentially you have 2 types of partitions. One should be valid, as in that input is valid, and you have another type of partition which is invalid. So for example, say you have a program which asks for a person's age in integers, years and months. Let's say in this example we're asking for a person's year and months in order to vote in an election. What would be the valid and invalid partitions for those 2 inputs? So let's have a look at this. So the invalid partition for years should be anything less than 0. Okay, so you're probably thinking now, why isn't this 0, 18, if we're assuming someone is going to be 18 to vote? Well, we're not going to check here if something is invalid in terms of can they vote. We're just checking can the information be typed in. So before we check if something is valid in terms of the logic, we're checking to see if the value they typed in makes sense for that input. So it doesn't make sense to type in something that is less than 0 for the years, because someone can't be -5. So we need to make sure that they're typing in something that is less than 0, just as an input. So something that is 0 or more should be valid. And notice there we're specifying this, infinity symbol here. So obviously we could say, years is a valid input between 0 and 120. But who decides what a valid age is, really? Someone could live to 121 for all we know. So what we're doing there is we're just assuming that the valid partition is a positive integer, or 0 or more. Okay, so if a person types in 0 for the years and 1 for the months, that should be valid in terms of an input, and then we can look at those inputs and decide if they're valid for our specific case, i.e. are they eligible to vote. And then when we get down to the months, we've got two types of partitions here in terms of valid and invalid, but we've got two invalid partitions here. So if we read this in plain English, we're essentially saying here a value from 0 to 11 inclusive is valid, anything that's less than 0 is invalid, and anything which is more than 11 is invalid. So the reason we've got 11 there is, let's say someone is 18 years old and 12 months old. 18 years old and 12 months old just means they're 19, okay? Because as soon as they reach 12 months old, that means they've reached another year older, okay? So again, if we're checking two inputs, year and months, those would be the valid partitions there, and then you would do some additional checks to see if that's suitable for your case, okay? So tests are now designed so that each of the partition is covered by at least one test. So this one here has two partitions, invalid, valid. This one's got multiple boundaries. So this one has 0 to 11, which is valid, and anything less than 0 is invalid, anything more than 11 is invalid. Now, how do we choose the values for these partitions? How do we actually decide what is a sensible value? So a common approach is to use what's known as boundary value analysis, which is where we choose the test values based on the boundaries of those partitions. So if that doesn't make sense, usually when we have code which is testing things at a boundary, it makes sense to choose values which are representative of an equivalence class. So for example, with that month input on the last slide, we know that -1 was going to be invalid and we know 0 was going to be valid. So it makes sense to test those values at those equivalence partitions or those boundaries. And on the opposite end, 11 is valid for a month and 12 is invalid. So it makes sense to check things on either side of that boundary, 11 and 12. Because as you saw from one of those first quotations, bugs tend to congregate at boundaries. So that's why it makes sense to test boundaries. So in terms of a worked example, you'll be working on this example inside the portfolio for this week. So let's say we're writing a test plan for some code which calculates the interest for a certain type of bank account. The specification here is two inputs. So the first input will be a deposit of how much someone's going to deposit to the bank account, and that's going to be a non-zero integer amount in pounds up to the maximum deposit amount, and I'll tell you what the maximum deposit amount is in a second. And then the term is going to be a term in whole years, at least 1 year and up to and including 10 years. And then the output will be a value in terms of how much will they earn, how much will they net in interest, including the amount they deposited after the term has elapsed. So the interest rate depends on the initial amount as follows. So again, there's going to be two inputs. One's the deposit, the other one will be the term, and the output will be the interest that they've accumulated, including the deposit. So this handout is available on Moodle. It's the test plan exercise solution, and this just goes through a fully worked example. So this will help you out for the portfolio. If we just go back to the presentation a sec, So the first stage is to write out the equivalence partitions for each of the inputs. So for example, what would be the equivalence partitions for deposit and term? So as you can see from those descriptions, you've probably guessed what those are. So if we go back to that worked example, I'll show you the solution for that now. So part one is to get the equivalence classes, or the equivalence partitions, and as you probably guessed, the valid equivalence partitions for deposit, they can deposit 1 to 1,000 based on that example in the slide. 1,000 to 1 to 10,000 is valid, 1,000 to 1 to 50,000 is valid, which means those invalid equivalence classes is anything less than 1 or anything more than 50,000. And then similar thing for the term, we've said a person can deposit money for at least 1 year up to and including 10. So we're including 10 in that valid class there, a valid equivalence class. And then in terms of the invalid ones, it would be anything less than 1 and anything which is more than 10. Okay, and then going back to the presentation again, just look at part 2. So stage 2 is to write down all of the valid and invalid test values for each of those inputs using boundary analysis. So using values which are at the boundary of those equivalence partitions. So let's go back to the worked example, and as you can see there on part 2, we've got some boundary values there. So we want to check for ones which are included and also values which are at the border. So because one is valid, we would check at the opposite end of that, or just below, but just before it, which is 0. And we know values such as 1,000, so those two are part of one equivalence class. So 1 to 1,000, and then 1,001 to 10,000 was part of the other equivalence class. And then 10,001 to 50,000 was the maximum they could deposit, and that's part of the final equivalence class. Which essentially just means the invalid values, if we were to go at opposite ends of those boundaries, because 1 is the minimum, the boundary there, if we go to the left side of that, is 0. And because the maximum value is 50,000, if we look at the other side of that boundary, we'd have 50,001. So those two, we could check for those inputs, and those would be where the common errors lie. And then exactly the same again with term. So you could say 1 and 10 is valid for those equivalence classes. And then 0 and 1, again, you check in the other side of those equivalence classes. And this would give you a test plan, which is part 3. And you would just say, for example, let's say someone deposits £1 over 1 year. That's not going to net much interest. They would just get their pound back. And then you'll see at the bottom here, there are some cases which don't actually return a value. They return an error. So for example, that deposit, that's an invalid value, isn't it, for that equivalence class, that partition. So that should return an error regardless of how long they're depositing that money for. 0 is an invalid deposit, so we'd return error there. And then same again with this deposit here. We've said the maximum deposit amount is 50,000 and they're trying to deposit 50,001. So just because one of these inputs might be valid, if one of the inputs is invalid, we need to return an error. So inside the portfolio for this week, you're actually going to implement a class which tests for these different cases and implements logic and then returns the expected output. So if a person passes in 1,000 for the deposit over a 10-year period, they should get that interest rate back plus the amount that they deposited. Okay. So don't forget the interest rate is inside the presentation, and you'll also be able to see it up here. Okay, so that's where you'll find the interest rate for each of those deposit amounts. So let's go back to the presentation. Okay, so after you've done stage 1, which is the equivalence partitions, you'll then establish the valid and invalid boundary values, and then after you've done that, you can then actually create a test plan which uses those valid and invalid boundary values. Moving on to white box testing. So as I said before, white box testing assumes that you know the internals of the code, so you've got knowledge of the code, whereas black box testing is where you don't have knowledge of the code. So typically we can use three types of white box testing. So the three that I'm going to talk about quickly are statement coverage, branch coverage, and path coverage. So the first one, statement coverage, involves executing the test results in all reachable program statements being executed. And this is quite weak in the sense that it's not going to cover a large portion of our program. It's just going to cover, some specific statements. But it does have the advantage that it can automatically be reported on during runtime. So, we could add some print line statements, for example. So as you probably know, it's quite weak because it's just testing or covering some statements. Improving upon this slightly is what's known as branch coverage. So we're executing the test results in branch conditioning, taking all possible values. So, every branch should be either true or false. We may not follow every branch. We're just testing specific branches to see, are they evaluating to what they should be evaluating to? And then one deeper than that is path coverage, which involves executing tests covering all paths through the code. So all possible combinations of branch conditions. This is not really achievable in large portions or large applications because you may have loads and loads of branches, each delving off into different areas of the program, and your application may be simply too big in order to converge or cover all the paths that your program has the opportunity to take. So 100% path coverage is often impossible to achieve. Again, as I said, on our small applications we can achieve it because our applications are typically no more than 100 lines of code, depending on how many classes we've got. So typically we can achieve it in the labs, but for these bigger applications it's very hard to achieve. So in terms of testing games, as you can imagine, games are quite messy because they have a huge amount of variables on the go and a huge amount of possibilities and combination of inputs. So also the scale of a game. So MMORPGs, massive multiplayer online role-playing games such as World of Warcraft, EVE Online, Guild Wars 2, all these MMORPGs, they have just such a huge amount of inputs and variables to consider. But we can still use principles of black box testing to test these games. So one way is to perform compliance testing, which is where we're checking, this is typically carried out by the platform holders, so the people who actually own the game, that the game meets functional standards, and standard test plans are produced for this. So if this happens, what are we expecting to happen? What is the output? And then fixing it if it's not the intended output. And then the second type will be functional testing, which is where we're checking to see if the game plays as intended. And then that's usually with reference to the requirements, which is the design. And typically that's performed by either the publisher of the game, it could be in-house, it could be external, it could be a dedicated Q&A team. When I say Q&A, that's quality assurance. So it could be, if it's a big company, they'll usually do that in-house. So, the company that makes World of Warcraft, Blizzard, they'll have a in-house team that is actually testing that it meets the functional requirements, and then they may do some extended testing after that, which is beta testing. So testing, there's loads and loads of different types, and we've covered a lot of those types. And just to extend functional testing for games, as I said, we could look for equivalence partitions and boundary values in games testing. So for example, if we let a person buy some bullets or ammunition for a gun, we could test some boundaries there, such as, if we let them buy 1 to 1,000, we'd test some boundaries there. We'd say, can they buy 1,001? Can they buy 0 bullets? Can they buy -1 bullets? So anything that's quantifiable should be tested. So things like scores in a game. If you shoot a zombie, you'd expect the zombie to die or disappear, and you'd expect your score to increase by some amount, such as 100. And then you'd want to perform testing on things such as the user interface and menus. So we're testing for functionality there, i.e. does the interface work? For example, if we're going to have a menu for the sound and graphics, or loading or saving a game, can the player pause the game? Can they enter the options menu? Can they enter a sound value? Can they set the volume to 0? Can they go back out of that menu and then back into the previous menu and then resume the game. You'd expect all the game sounds to be muted if that does work. And then in terms of writing test cases for a game, for example, if you're writing a test plan for your assignment, one of the first things you might test after you've completed the game is, does the splash screen work? Can they enter the game? So that could be your first test case. You could test to see if the user can start the game. You'd expect when the user presses the space bar that the screen is displayed correctly. So for this test case is starting the game, and you'd expect the splash screen to be displayed correctly. So that could say start the game, i.e. spacebar. And this test case here would spawn 2 additional test cases based off that. So once we're in the splash screen, in order to test if the game starts, we could test to see if a person presses the spacebar, does it start? And then all other inputs should be invalid. So test number 2 could be when you're on the splash screen, if a person presses keys other than space at random, that should provide no effect. The splash screen should still be displayed correctly. On the other hand, or the other case, if they're on the splash screen and they press space, that means that's a valid input and the game should start normally. Okay, I talked a lot there because it's 52 minutes, this video. So I talked a bit about the assignment and the portfolios, summarised the 4 stages of testing: unit testing, integration, system and acceptance. Then we talked about those 2 more broad categories of testing: white box and black box testing, which refers to the level of knowledge of the code used when designing the tests. And then we looked at 2 methods of actually performing those tests, which was equivalence partitioning and boundary value analysis, and those were techniques for efficiently covering the inputs with tests which are likely to find errors. So again, as that first quotation said, bugs tend to congregate at boundaries, so it's quite common that a bug appears at a boundary of an input. So we usually test those boundaries. And that is the last slide, which means I'm done talking now. So there is a lab on testing and there is a portfolio on testing, so this lecture is quite important in that regard, in the sense that we do have a portfolio. You're not required to produce a test plan for your assignment, because if you look inside the assignment brief, that's not a requirement. But you should still test your game before you submit your assignment, just to make sure everything works. So it is good practice to make a test plan. You don't need to submit one, but maybe make one and just make sure that everything works as intended, and you are checking those different boundaries just to make sure your game is in a workable state. And that's it. So make sure you're utilising the drop-in sessions as always: Monday, Wednesday, Friday, 12 to 1. And those drop-in sessions are running in week 18 for Tutor Week. So make sure you are turning up to those. And that's it for this lecture. Thank you.